Hello, Chemistry 12. Today, what I wanted to do was focus on something that we use in titrations, which are indicators. Now, I had touched upon this last day or last lesson when we did this little diagram of how we use titrations. And what I want to do is I want to focus on this indicator. Now, some of you have already been exposed to indicators before, right? Either in grade 10 or in Chem 11 or whatever. But what I wanted to do is I want to focus on what are indicators and talk about that in terms of proton donation and so on, in terms of acid-base chemistry. So indicators are substances that change color with a change of pH. Now, how do they do that? They lose or gain protons at different pH values. So depending on the acidity of the solution, what it does is it causes the indicators to lose or gain protons. Now, in this particular scenario here, where we have this phenolphthalein, okay, it says 8.2 is clear and 10.6 is pink. So what does that mean is that it means that if the pH is from 0 to 8.2, all right, what happens is from 0 to 8.2, it's going to be clear. There's no change. And from 10.6 all the way to 14, what you have is a pink, or we call it a red. Okay? And in between the two, this is where we get light pink. Okay? Now, for bromthiamyl blue, what happens is it's 6 will be yellow, 7.6 will be blue. So what that means is if you have a pH of 0 to 6.0, the bromthiamyl blue solution will be yellow. Okay? And everything from 7.6 and beyond up to 14, this will be blue. And in between is you are going to have green. Now, if you take a look on page number 7 in their data table, what you're going to see is you're going to see a whole range of different indicators. Okay, so if we look at our indicator chart, okay, so what you have is you have the different indicators down the left-hand side. Let me just clean this up a little bit. Okay. And so what you have is you have the indicator on the left-hand side, this pH range down the middle, and the color change down the right-hand side. So depending on the indicator, so let's say, for example, methyl orange, the pH range is 3.2 to 4.4. It goes from red to yellow. So that means if you take a look, if you went from 0 to 3.2, that would be red. And then 4.4 to 14, this would be yellow. Okay. Now, if we take a look, I have the same thing, but I have a little bit fancy picture. You can have it on this sort of pH range. Now, most of the indicators that you have only have one color change. But one thing you should notice is notice thymol blue. Thymol blue, there's one up here and there's one down here. Thymol blue actually has two color changes. It goes from red to yellow down here, and it goes from yellow to blue up here. Now, notice it says thymol blue base range and thymol blue acid range. In this case, for thymol blue acid range, it changes the color at a pH less than 7, while thymol blue base range, it changes colors between in the base range, in the pH of greater than 7. Now, if you look at your chart, you will see that down here. So what you have is you have your thymol blue, and I had just erased it. This is the acid range. And if you take a look, there's thymol blue again. Here is in the base range because it changes color, pH base range here. Okay. Because it changes colors from yellow to blue, pH greater than 7. All right. Now, if we focus back on indicators, the color changeability is due to the fact that indicators act as a weak acid base equilibrium. And the key difference between indicators and regular weak acids or bases is that the different molecules have different colors. That's the only thing that is different. Okay? You treat them exactly the same as weak acids or weak bases, but the only difference is that the acid and its conjugate base, or the weak base and its conjugate acid, have different colors. Now, if we take a look at bromthymol blue, now this is the weak acid equilibrium up here. So here's your equilibrium. Whoopsie. Here is your equilibrium. Now, we have this HIND. So HIND is just the generic form of an indicator and the acid form. So why do we call it the acid form? Because have H plus. Okay, so you notice here that there is a hydrogen. Okay, now here is considered the indicator, but the base form, and the reason why it's a base form is because it is missing H plus. That's why it's called a base form. All right, is because it's missing the H plus. So how does this indicator work? So in an acid solution, the indicator takes on the acid form. Why? Is because the H3O plus is high from the acid solution. Okay? Now, when we talk about acid solution, it could be like HCl or HNO3 or something else. Therefore, Le Chatelier drives the indicator's equilibrium to the left. So what happens here is if we take a look at this, you increase the H3O plus equilibrium. And then, so what happens is, going back to Le Chatelier, it drives the equilibrium to the left. And this is why you get the yellow form. So for bromthymol blue, anything with a pH less than 6 will drive the H3O plus higher and force the equilibrium to go to the left. And so this is why bromthymol blue will be yellow between a pH of 0 to a pH of 6. Okay? Now, because indicators are weak acids bases, they have a Ka expression. So again, you have a Ka just like exactly the same as what we had done before, where you have, where is it? You know, we have a Ka expression, in this case for HF. So what we have is we have a Ka expression, but specifically talking about an indicator. Okay? Now, the one thing about this for indicators. When indicators reach equivalence, where you have the moles or the concentration of the base is equal to the concentration of the acid for the indicator, this is called the indicator's transition point of that particular indicator. Okay, so when indicators reach equivalence, where you have the moles or the concentration of the base form is equal to the concentration of the acid form, this is key. This is called the transition point of the indicator. Now, we've talked about equivalence point before when we did indicators, okay, where we said moles of acid is equal to the moles of base. But in this case, when we're talking about equivalence point, we're talking about the base form equaling the acid form. This is the transition point of the indicator. Now, what's the significance of this? So if we were to write the equilibrium for an indicator at H3O plus and IND minus 1, all over concentration of HIND, at equivalence, can cancel the indicators. Concentration. So I can cancel here, I can cancel here, and so what I get is I get Ka is equal to concentration of H3O plus. So what's the significance of this? It means that an indicator will change color when the H3O plus is equal to the Ka. Why is it changing color? Is because if the base form and the acid form are exactly the same, what happens is they can cancel out. And this is why if we went back to bromothymol blue, when it's changing color, this is why you have the intermediate color of green between 6.0 and 7.6. Because what's happening is the acid form and the base form are starting to be equal. All right. Now, what I'm going to do is I'm going to give you a couple of questions, and then that will be it for today's lesson. Now, it says calculate the chlorophenyl, the Ka for chlorophenyl red. In other words, calculate the Ka when the indicator changes color. Now, the first off, for chlorophenyl red, you need to find the pH range. So if you look at your indicator chart, and what you do is you try to find the pH range for chlorophenyl red, you notice it is 5.2 to 6.8. Okay, so here the pH range is 5.2 to 6.8. Now, what you want to do is you want to find the midpoint. So this will be 6.0. I will call this the perfect transition. Yep, see. Now I call it the perfect transition because it's right in between that pH range. It's hard to measure, so we just have to take an estimated guess. So since the pH is equal to 6.0, therefore the concentration of H3O plus is equal to 10 to negative 6, and this will be equal to the Ka value. Because remember, at the transition, that's when the Ka is equal to H3O plus. Okay. Now, so that's one question. Another question we could ask is estimate the pH of a solution in which brom cresol green is blue and thymol blue is yellow. So what we can do is take a look at our table. So brom cresol green, if we were to take a look here, brom cresol green, notice 3.8 to 5.4. Okay, and we have thymol blue. Well, we'll take a look. There's two thymol blues, so we have to figure out which one are we talking about. Is it the one here or the one here? So there are many different ways of doing this, but I like to do it in sort of a table format. So what we have here is 0. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, so brom cresol green is blue. So we look for brom cresol green. Where's brom? Where's my indicator chart? Brom cresol green is blue, so that means here 5.4 and above. So if we look at our chart, we go, okay, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So here, I'm going to put it in blue. So brom cresol green. So we know everything from 5.4 and above will be blue. Now it says thymol blue is yellow. So in this case, if we look at our indicator chart, thymol blue is yellow. So in this case, if we look down here, it's yellow, everything below 8. So if we go back to our chart, so everything here, if we go 8 all the way to here, this will be yellow for thymol blue. So in this case, what I want to do is I want to look for the overlap, which is right here, where the two overlap. So the range in this case is 5.4 to 8.0. Now, there's many different ways to do it, and depending on which textbook you use, right, or what videos you watch, there's many different ways of doing it. But I like to do it this way because I'm a visual learner, and this will help me figure it out. All right, the last question. It says, determine the color of phenolphthalein in 0.5 molarity HF. Now, the first thing we need to take a look at is we need to recognize, is HF a strong acid, weak acid, strong base, weak base? So again, we go back to our acid-base chart. And here, if we look for HF, where's H? HF is right here. Notice it's a weak acid. So if we were to take a look at our indicator, here it's a weak acid. And because we have to do calculations, therefore we have to use ice tables. Yay. So again, what you would do is you would go HF plus water is in equilibrium with H3O plus and F minus 1. We set up our ice tables. Come on, there we go. So we have ice. So here we have 0.50. This should look familiar. Oh my gosh, minus x, plus x, plus x. And then you have 0.50 minus x, x, x. And then you go, okay, Ka is equal to concentration of H3O plus, concentration of F minus 1, all over concentration of HF. And you solve. So concentration of H3O plus is equal to, let me see, HF is 3.5 times 10 to negative 4. Okay. So 5 times 3.5 e negative 4. And then you square root it. So here would be 0.0132 molarity. Okay. Then you would go pH. You take the inverse log, would be 1.88. Now for pH of 1.88, if we look at our indicator chart for phenolphthalein, so here, phenolphthalein, the range is 8.2. Let me erase this for here. Ooh, yeah. Let me just erase this here so that's a little bit clearer. Okay, so the phenolphthalein here, we look at the color. So it's 8.2 to 10 is colorless to pink. So since it is 1.8 for HF, phenolphthalein is clear. Okay. Now, some of you might say, wow, that's a lot of work. Not really. This first part you've done. Okay, this ice table, solving for H3O plus, you've done that. pH, you know how to calculate that. Negative log, whatever. All you're doing is you're just looking at the indicator chart to see where this pH range is. All right, so we're just slowly adding on to stuff that you have learned before. All right, ladies and gentlemen, thank you very much. Have a good day. Bye-bye.